So, we shall continue with this the discussion on perturbation theory that we have been doing, and in particular we are talking about the time independent perturbation theory and a non-degenerate case. And just to remind you that the perturbation is small compared to the unperturbed Hamiltonian, and hence we are allowed to use the eigenstates of the unperturbed Hamiltonian in order to find corrections to the energy and to the wave function. And we shall continue with that discussion, and then we will talk about the degenerate perturbation theory. If you remember, the wave function correction involved an energy denominator, and these energy denominator came as some En0 minus Ek0. Now, that would blow up or will diverge as En0 equal to Ek0. So, you need an alternate formalism for this degenerate case, and we will do applications of the degenerate perturbation theory, and in particular we will talk about Stark effect, which is a hydrogen atom present in presence of an hydrogen atom in presence of an electric field, a weak electric field, which does not cause ionization, but it causes change in, or rather the split in degeneracy and so on. Okay. So, let us start with an example so that you get a handle of how these perturbation theory problems are handled. So, we are talking about a particle in a box. So, this is the same problem that we have done. So, you have V equal to 0 here, and V is infinity at the walls, which means that the particle is actually trapped inside. And the question is that suppose you have a perturbation of the form which is epsilon V naught sine pi x by L. There is no need for both epsilon and V naught, but just V naught is the scale of the, it has a scale of energy, and epsilon is much smaller than 1. That tells you that this is a perturbation term, and you want what is the correction in energy to the n equal to 2 state, which means the first excited state. Okay. That is the question, and the answer is simple, because what you have to do is that you have to calculate the energy correction. So, that is the answer, which can be obtained by this unperturbed energy for the n equal to 2 state, and you have the H prime and then this, and this can be written as 2. So, we will use this n equal to 2 state as root over 2 by L sine 2 pi x over L. Okay. So, 2 epsilon V 0 and divided by L, and then we have sine square 2 pi x over L, and you have a sine pi x over L and integrated over dx, and this is from 0 to L. So, we have to integrate this thing from 0 to L. If you look, if you do this integral by converting the sine square into cosine and so on, I leave that integral to be done by you, and then what you get is that you get a 32 epsilon V 0 and divided by 15 pi. So, that is the energy correction to the second excited state. So, if the second excited state, which has the unperturbed energy equal to 4 h cross square by 2 m L square. So, it is basically the unperturbed energies are given by n square pi square h cross square. So, I missed a pi square here, and so 2 m L square. So, n equal to 2. So, that gives you a 4. So, 4 pi square h cross square divided by 2 L square. So, the total energy will become equal to E 0 plus the correction that we have found out, which is E n 1. So, this is like 4 pi square h cross square divided by 2 m L square plus 32 epsilon V 0 divided by 15 pi. That is the answer for this, and this term is purely coming because of the perturbation. Okay. There is a contribution to H prime. So, let us go into the degenerate perturbation theory, which has to be, as I said, that it has to be dealt with care. And so, what we have is that there are several energy states that correspond to several states, wave functions, they correspond to the same energy. So, this is called as a degenerate perturbation theory. Okay. So, the earlier formalism that you saw was really appropriate for non-degenerate case when all the levels are non-degenerate, but of course, we know that as you go in 2 dimensions and higher than that, that is larger than 1 dimension, degeneracy is bound to come, and we have shown that for say particle in a box. And so, particle in a box, let us just sort of once again remind you that how the degeneracy comes is that this is what the energy would be proportional to this n square. So, we can have this as 2 1 1, 1 2 1 or 1 1 2. All these 3 will be degenerate because each one of them will give rise to 6 n square equal to 6 and so on. I mean in the sense that all of them will have the same energy, which is n square, which is 4 plus 1 plus 1, that is 6. So, it is like 6 pi square h cross square over 2 m l square, but they would correspond to different eigenstates of the problem, because this would be like sine 2 pi x over L, sine pi y over L, sine pi z over L, and the other one, the second one would be sine pi x over L, sine 2 pi y over L, and sine pi z over L. And the third one, the last one, would be sine pi x over L, sine pi y over L, and sine 2 pi z over L. Okay. And these are distinct eigenfunctions, but they correspond to the same energy, and this is what is meant by the degenerate case, and we have to develop a perturbation theory for this degenerate case. Okay. So, we still have these states, okay, which we call as psi n 0 and psi m 0. These are all orthonormal, and if you use some other indices such as what we are going to use here. So, we make a postulate for the total wave function is that we have a psi n, and there is a sum over I a I psi n I 0 plus sum over k, which is not equal to n, and we have a c n k lambda, and then sum over I b I and psi k I 0. Okay. And that is your ansatz for the wave function. And so, we have used another index, as you see here, in addition to the n and m or n and k here, we have used I index, and that index would correspond to different eigenvalues. Okay. So, there are these eigenvalues which may be degenerate, and these would represent this eigenvalue index. And so, what we have done is that we have gone from a psi n 0, which was written earlier, to these sum over I a I psi n I 0. These are still the eigenfunctions, degenerate eigenfunctions corresponding to eigenvalue say lambda I, and that is why there is a sum over I and AI. AI is just an amplitude of the wave function which need to be determined, and the C n k lambda, these are powers. This can be expanded in powers of lambda, and you keep a certain, you evaluate this Schrodinger equation till a certain power of lambda, and this power of lambda would eventually talk about, or rather give us this the order of perturbation theory that you are dealing with. Okay. So, AIs and BIs, as I said, are the coefficient that we need to determine, and of course, the C n k alpha as well. So, once again what we do is that we will put it into the equation, which is H psi n equal to E n psi n, and use this as the expansion, and E n is also expanded in terms of lambda. So, till first order we get a term which is H 0 and a k not equal to n, and you have a C n k 1. So, what I mean by first order is that is first order in lambda, just the way we have done it for the non-degenerate perturbation case. And then there is a sum over I b I psi k I 0 plus H prime sum over A I psi n I 0, and this is equal to E n 1, which is what you want, that is the first order correction to energy. And so, basically the E n is equal to E n 0 plus lambda E n 1 and so on. Okay. So, we are equating till the first order of lambda, and E n 1 sum over I A I psi n I 0 E n 0 k not equal to n, and C n k 1 and sum over I b I psi k 0 I. It may look complicated, but the final result that we are going to get is not difficult, and it is easy to actually reproduce, or rather get the first order correction, very similar to what we have done it for the unperturbed case. So, just bear with me for some time, because these are essential steps and they cannot be avoided, especially for these degenerate perturbation theory. So, what we need to do is that we need to actually calculate this E n 1, and to get the E n 1 we follow the standard procedure of taking an overlap with this psi n with another index, I mean in the sense that psi n 0 j. So, let me write that. Okay, so, what I mean by this is that you take this term, okay, so the conjugate of that, and recognize that your E n 1, then E n 1 is extracted, and because k is not equal to n and all that, we get some of the terms going to 0 as it happened earlier. So, this is like a psi n j 0 h prime psi n I 0 and so on, and this can be called as the matrix element H prime j I. Okay. So, between the eigenstates of the unperturbed Hamiltonian, and this is the energy correction, and that is exactly what you need. Okay. So, this is the energy correction. Now, instead of just a number, this was exactly like what we have done it in the example. You saw that we have used this. Now, because of the degenerate case, we have a sum over I, and there is also an associated amplitude that need to be determined. Okay. So, this can be written as, so this A j E n 1. So, there is a A j which I forgot here, So, there is AJEN1, this is equal to sum over I. Now, this sum over I now has to be specified that this is, I told you that this actually is the eigenvalue index. So, it will go from 1 to D, where D is the degeneracy. Suppose this n equal to 2 state is 4-fold degenerate in the hydrogen atom without leaving out the spin degeneracy. If you include that, it becomes 8-fold degenerate. So, D is that number, like in this example that we have talked about, the n equal to 6 or rather n square equal to 6 is actually 3-fold degenerate state. Okay. So, because 0 is not allowed, so they can either take values. So, this is the first excited state. Okay. So, this is I equal to 1 to D, and we have a AI and a H prime JI. So, that is a matrix element has to be considered, and the sum over I runs from 1 to D, and D denotes the, as I said, it is a degree of degeneracy. So, that is what is important, and the problem becomes slightly more complicated as compared to the non-degenerate counterpart, but then nevertheless it is a finite dimensional problem and we should be able to solve it, and we will just see it for a given case. So, let us do a 2-fold degenerate case. This is the simplest, I mean 1-fold is the non-degenerate and 2-fold is the degenerate, the first, the simplest of the cases. So, 2-fold degenerate case. And what we have is that we have this H0 minus En0 psi n 1 is equal to En1 minus H prime and a psi n0, and then of course, so this is the equation that we have, that is the starting point, and let us call this as equation 1, and the psi n0 is, so this is at the first order. Okay. So, we are really developing this 2-fold degenerate case at the first order, and in fact, anything beyond first order is little more complicated. We will see some examples, but may not solve them completely. So, this is the equation that we start with. This is the first order equation. If you go back to where we started discussing non-degenerate perturbation theory, you still have this, this equation written down there. So, now the psi n0 comprises of 2 orthogonal eigenfunctions. Let us call them as u1 and u2, and let me write them as a1 u1 plus a a2 u2, where a1 and a2 are in general complex coefficients. So, so these u1 and u2 are the degenerate states. That means, they are themselves distinct, they are not equal to each other, neither they are linearly dependent. So, they are linearly independent and they are orthonormal, and they form these bases for, or rather these two are the degenerate state, they correspond to same energy. Okay. And so, this is like the answers that you do, and because you know that you are dealing with a 2-fold degenerate case, say for example, a 2-dimensional oscillator. Okay. So, a 2-dimensional oscillator will have a nx plus ny plus half corresponding to each of nx and ny, h cross omega, that is the nx ny energy. Now, if you talk about 3 h cross omega energy, so energy equal to nx ny equal to So, this is 1. So, let us talk about 2H cross omega. So, that is the first excited state, 2H cross omega. This is just an example. Then Nx can become 0 and Ny can become 1, or Nx can become 1 and Ny will become 0, and these two will give rise to a two-fold degenerate state, and which is very similar to the one that we are talking about. And so, this of course is equal to 1. So, 1, these two put together will make it 1. So, and nevertheless u1 and u2 are orthogonal because the corresponding wave functions are they are orthogonal to each other. These are these Hermite polynomials multiplied by the Gaussian function, and they are orthogonal. So, similar to that. Okay. So, we have to put it there in this equation on the right hand side, and let us call this as equation 2. And so, putting 2 in 1, what we get is the following. We get H 0 minus E n 0 psi n 1. My sincere advice to all of you would be that do it by hand. I am pretty sure that I am not making a mistake, but even if I do, with some either some sign or some index, that should not percolate into you. So, you should do it by all by yourself and convince that these are the correct steps to follow. And specifically I am doing it while I am speaking for the reason that you understand if I show you some slides, and then the idea would never get across, because these are mathematics that you need to do in order to arrive at the results, which are very important for us. The end results are important, but for you it is also important how you arrive at those results. So, H 0 minus E n 0 psi n 1, that is the left hand side, which remains unchanged, and then you have a E n 1 minus H prime, and then we will put this A 1 U 1 plus A 2 U 2. And understanding is u 1 and u 2 is equal to 0. So, that is a overlap or the inner product is equal to 0. Okay. So, this is equation 3. Now, what we can do is that we can take an overlap. So, when I say overlap, what I mean is that you operate it by this conjugate of some wave function. In this case, it is a conjugate of u 1. That is the brow of u 1. So, if you do that, so operate it with this on both sides. So, this will be H 0 minus E n 0 and a psi n 1, so E n 1 you do not need to worry about because it is just a number. So, this will be E n 1 and this u 1, and then u 1 overlap will give you 1, and u 1 u 2 overlap will give you 0, but nevertheless you have a u 1 h prime with a 1 here, h prime u 1, and there is another term which is so that is a minus term with a 1, this is equal to 0, and then you also have a term which is minus u 1 h prime with a 2 coefficient h prime. I hope these are they do not look like. So, this, let me write it again. So, this is actually a 1, a 1, a 2, and then you have a u 1 h prime u 2. Okay. All right. So, now calling these ones as h prime 1 1 1 1 because that is a matrix element between these states, the unperturbed states, unperturbed degenerate states. This is h prime 1 2. Okay. And we will do the same thing for u 2, but look at this that H0 acting on H0 will act on this U1 and give me En0, which is its eigenstate. So, let me write it here. This is just an example. So, let me put a red line so as to this is just an example that we have given. Okay, so, this is separate, and so with this you also have H0 and U1 that is equal to En0 U1 and so on, okay, and H0 U2 is same as En0 U2. So, that tells you that this term is equal to 0, because H0 acting on this bra U1 will give me En0 and the En0 will cancel with this. So, what we have is 0 equal to En1 A1 and let me also put A1 1, okay, because we are talking about the first order. So, A1 1 and minus H11 prime A11 and minus H12 prime A21. Okay. So, this is the thing that we get, and if we do a simplification of that, these 1 along with A1 and A2 we have not written that earlier, but then it just sort of gives you a handle to remember that you are doing a first order perturbation theory. Okay. So, what you can do is that you can also leave that if you want, and it is not very essential to have it, but you can carry on with this if you wish. So, A1 1 this is En1 minus H11 prime, this minus A2 1 H12 prime, this is equal to 0, and let us call that as equation 4. So, this is what we get by just to remind you of the steps that we have written down the Schrodinger equation at the first order, that is first order in lambda, which is the smallness parameter, and then because of this degenerate case, this is the ansatz made for the degenerate case, that is you have the two degenerate eigenstates U1 and U2, which are mutually orthogonal, and they both give rise to energy En0. So, we write that ansatz there, expand it, and use shorthand notations for all these matrix elements of H prime between U1 U1 and U1 U2 as H11 prime and H12 prime respectively, and then simplify this to arrive at 4, which gives you one equation which is useful for us, and that contains these amplitude, and because we are talking about first order, so everywhere this En1 etc., the 1 in the bracket, they denote that we are talking about the first order perturbation theory. Now, the same thing we can do it on equation number 3 and take an overlap with U2. So, this is taking overlap with U1 that is this, okay, and then we go to this and then say that taking overlap with U2. And once when you do that, you get another equation which is of the form A11 H21 prime and plus A21 En1 minus H22 prime to be equal to 0, and let us call that as equation 5. Now, you see you have now, instead of one equation for the energy correction, you have to solve a system of two equations. and these two equations can be solved if or rather they have a unique solution if the determinant corresponding to the coefficients of A11 and A21, that is A2 superscript 1 and A1 superscript 1, the one inside bracket, these coefficients vanish, or the determinant of the coefficients vanish, and so we write for a unique solution we should have this condition, that is En1 minus H11 prime, H12 prime and minus H21 prime and En1, that is the same, En1 minus H22 prime. Okay. So, this should be equal to 0. I mean, this means that the determinant is equal to 0. So, this is actually the determinant. I mean, determinant is usually written between two vertical lines. So, we will just do that. So, this is equal to 0, and this has two solutions which are the solutions for En1. So, we will write En1. So, this 1 means that there are two solutions, the one in the subscript of n, that means that there are two solutions, and we are talking about En1 and En2, but the superscript inside bracket, that tells you that we are talking about the first order perturbation theory. So, make all these nomenclature clear in your mind, and then we have H11 prime plus H22 prime by solving the determinant equal to 0 and plus a root over of H22 prime minus H11 prime square plus 4 H21 prime square. So, this is 1, let us call it as equation number 6, because we already have 5. So, and the other one is H11 prime plus H22 prime, and comes with a negative in front of this square root. So, it is H22 prime H11 prime square plus 4 H21 prime square, and the bracket closes. So, that tells you that these are the two energy corrections. We did not have a single algebraic equation to solve in order to get En1, but it came as a matrix equation, and for a unique solution the determinant of the coefficient matrix will have to vanish, and that gave us these two corrections to the energy. So, suppose you have these energy levels which were earlier degenerate. Now, because of this plus minus sign, it sort of splits like this and like this. So, this is unperturbed En0, and these are the energy corrections. Let us call it as a En1, and let us call this as the En2 1. Okay. So, the degenerate energy level now, because of this perturbation, that splits, and the splitting is apparent because of this plus and minus sign. Now, for some reason inside this square root these terms somehow vanish, then of course, there is no splitting of degeneracy, but mostly what our experience says is that there is a split in degeneracy unless some other selection rules that prohibits that there should be no split in degeneracy. We will talk about that. Now, in order to calculate the change in the wave function, we can calculate these amplitudes which are A21 divided by A11. This is equal to 2H2 prime. So, this is like putting 6 in 4 and so on. Let us write that. So, equation 6 in equation 4. So, 2H21 prime divided by H11 prime minus H22 prime plus root over of that, and we have H22 prime minus H11 prime square plus 4 H21 prime square and so on. Okay. So, this is equation 8. So, that is the first order correction to the amplitudes, which will eventually give this the change in the wave function, but this appears in the ratio of these two coefficients at the first order level, but do not forget that there is another equation coming from the normalization condition, which makes it the other equation. So, which means that the A11 mod square plus now this mod square does not have any meaning because this real if all these H primes or the matrix elements of H prime are real, but we still write it notionally as mod square, and this is A21 mod square is equal to 1. So, these two equations will allow you to solve this problem, and putting 7 in 5 we have, so this is 6 in 4 and 7 in 5. So, we have these A 1 2 divided by A 2 2, that is for the other eigenvalue. So, and this is with a negative sign, and 2 H21 prime, and we have this H11 prime minus H22 prime plus root over of H22 prime minus H11 prime square plus 4 H21 prime square and so on. Okay. And then again you have this A1 2 mod square plus A 2 mod square should be equal to 1, and these are equations 10 and 11, and put together all these energy corrections En 1 and En 2, which are written here. So, equations 6 and 7 here. So, equation 6 and 7 are the energy corrections, and equations 8, 9, 10, 11 are the corrections to the wave function, and put together they give you the entire problem, the solution to this two-fold degenerate problem. It is simple, but nevertheless you have to solve a matrix equation, a system of equations rather, and what is the dimension of that system of equations that you have to solve? That simply depends upon what is the degeneracy of your system, or what kind of what is the level of degeneracy and so on. So, now since we have done a simple problem, let me show you another one which is slightly more complicated and are directly related to the next problem that we are going to do, that is Stark effect. That is a four-fold degeneracy. So, four-fold degenerate state. We will not do a derivation of that, but we will write down the final results. So, it is a four-fold degenerate state, how to deal with that. So, let us say that we have now all these U1, U2, U3 and U4, all of which correspond to the same energy. Let us call that energy to be equal to some En0, and so your psi n0 is actually the so psi n0 is A1 U1 plus a A2 U2 plus a A3 U3 and plus a A4 U4. And it is almost obvious that that you have this four-fold degenerate problem. So, we will have four different energy corrections to each one of them, It may lift the degeneracy completely, or it may lift the degeneracy partially, or it may not lift the degeneracy at all. Say we are talking about n equal to 2 of hydrogen atom. This is an example. And without including the spin degeneracy, this is 4-fold degenerate, and we are really talking about that. So, all these n equal to 2 states of the hydrogen atom would have a structure like this. They all correspond to the same energy. Okay. So, we have this set of 4 equations which we have to solve. So, they are written following what we have done is H12 prime, A2 plus H13 prime, A3 plus H14 prime, A4 equal to En1 A1, and we have H21 prime, A1 plus a H22 prime, A2 plus a H23 prime, A3 plus a H24 prime, A4 is equal to En1 A2, H31 prime, A1 plus a H32 prime, A2 plus a H33 prime, A3 plus a H34 prime, A4 equal to En1 A3, and finally we have H41 A1 plus a H42 A2 plus a H43 prime, A3 plus a H44 prime, A4 equal to En1 A4. So, this is just a 4x4 equation which needs to be solved. So, the unique solution is determined by the fact that the solution is obtained, let us write it here, when the determinant of this vanishes. So, it is a En1 minus H11 prime, H12 prime, H13 prime, H14 prime, and then it is H21 prime, En1 minus H22 prime, H23 prime, H24 prime, and H31 prime, H32 prime, En1 minus H33 prime, and H34 prime, H41 prime, H42 prime, H43 prime, and En1 minus H44 prime. This has to be equal to 0, and I hope you understand that Hij or this H prime Ij is nothing but Ui H prime Uj. So, that is the matrix elements of the perturbation term taken between the different degenerate eigenstates of the system. So, this has to vanish in order to give us these 4 energy corrections. So, this will give us En1 1, En2 1, En3 1, and En4 1. So, this is the correction to different eigenvalues. So, this is the different eigenvalue index, and this tells about the order of perturbation theory. Okay, so once we get this, then the levels that are 4-fold degenerate, which are like this. Okay, so we are writing this as 4-fold degenerate, and then you can have a split in degeneracy as if like 2 will be shifted up and 2 will be shifted down, depending on these matrix elements and the solution of this. So, let us apply to a problem which we are, one usually does in this context, that's called as a Stark effect. And what is Stark effect? Stark effect is that the H atom, the hydrogen atom, which is the simplest atom, we have told this several times, there is one electron and one proton. It's is placed in a weak, and this word weak is important because we are going to apply perturbation theory, and it certainly does not cause any ionization of the hydrogen atom. So, the electron is never knocked out, and it remains very close to the ground state. So, that is the weak electric field, and want to find that what are the changes in the energy level. And we have discussed earlier that these can be, the hydrogen atom energy levels can be photographed in a spectrometer. So, if you, or spectrograph, and then if you see that this n equal to 2 line, which corresponds to say or n equal to 1 line, which is corresponds to minus 13.6 electron volt. So, n equal to 1 has an energy which is equal to minus 13.6 electron volt, let us call it E1. N equal to 2 has an energy which is minus 3.4 electron volt, which is this 13.6 divided by 4. How these different energy levels respond to the perturbation due to that electric field being applied is a weak electric field. Then the question is that how the hydrogen atom, or what degree of freedom couples with the electric field. Okay. That is the main question. And just to sort of a physical answer would be that you have, and this you must have done in classical electrodynamics, that there is an electron there. So, okay, and there is a proton there inside. So, this is like a dipole, because equal charges, equal and opposite charges are there at a distance, with the distance is nothing but the atomic radius, which is something similar to the Bohr radius. Okay. So, an electric field is, say, applied in this direction, and so this is the electric field, and we will write it as this curly E, because we do not want any interference with the energy, which we write as the normal capital E. So that there is no confusion that arises because of this notations. So, and this is, say, in the plus Z direction. This is just a a sort of notation that one uses for convenience. It really does not matter that which direction it is, but it is only in the Z direction that you do not have any azimuthal dependence, that there is no phi dependence. So, what happens is that because of this electric field, the dipole actually gets elongated, and so the dipole moment, which is nothing but the charge multiplied by the distance between the two charges, the magnitude of the charge and the distance between the two charges, this interacts with the electric field as a as a dot product. So, the potential energy that you get is the minus P dot E. Okay, and this is precisely what our perturbation term is, it is minus P dot E, and so this E is in the and P is nothing but, this is nothing but E R, okay, and R is a radial variable, and because there is a dot product, so this is equal to minus E E R cosine theta. Okay. So, there is a angle between the P and the direction of E, and that is why it is minus E E R cos theta, and usually because of this minus sign, and we have that electric charge to be also negative, we put a positive sign here. So, P is equal to minus E R. Okay. So, that is the understanding, and that minus sign gets cancelled, and we have these potential energy, or which is the perturbation term for us, and we have to calculate that what happens because of this perturbation, which is a product of the electronic charge E small e and the electric field, that's curly E, and then we have these radial variable r multiplied by the cosine of this angle. Okay. And so, the first question is that the simplest one, what is the first order Stark effect on the ground state of hydrogen atom? So, that is the question, and it is a valid question. So, what it means is the following, that the electron is assumed to be in the ground state of hydrogen atom. Now, you have applied an electric field and you want these energy minus 13.6 electron volt to shift up or down, and so the so down is not possible because you have a positive perturbation. So, it is going to shift up. So, whether it really does, and if it does, then by what amount. Okay. I told you this earlier that there is no real necessity that it will get shifted, and it may not, and in fact, it will depend upon a lot of symmetry arguments that if it does, if it does not, then there is some argument that is always there. And in this particular case, a priori I can tell you that there is no shift in the energy of these hydrogen atom in the ground state, and that is a non-degenerate problem. But nevertheless, what we can show that easily by writing. So, what is the ground state of hydrogen atom? It is called 100 state, where this is the N index, the first one, and then there is the L index, and then there is the M index. Okay. So, N equal to 1 means L can only take value 0, and if L is equal to 0, M equal to 0, that is the ground state, which has this energy which is minus 13.6 electron volt. And this is nothing but root over pi A naught cube e to the power minus r over A naught, where A naught is called as the Bohr radius, having a value which is very close to like 0.5 angstrom and so on. In fact, you can use this and take a mod square of this, which gives you the probability density, and you can ask this question that at what distance this probability density goes to 0, or rather it has it has a minimum value, or where this till what distance the hydrogenic wave function in its ground state is most likely to persist, and that answer is given by. So, you calculate P of r, that is the probability by taking the mod square of this psi 100, take a dp dr, put that equal to 0, and you will calculate r in terms of A0, r comes out as A0. Anyway, that is not the point that we are trying to make here. We are asking this question that what is this thing that is going to give you. So, it is minus 13.6 electron volt is the unperturbed energy, and we want to calculate what is En1. Okay. And because n is equal to 1, we call it E11, and this n is the index for the quantum number, or the principal quantum number that identifies which state it is in, and the superscript just talks about the order of correction in energy. And now the matter is simple, because you have to just take a psi 100 star r, and then you have this perturbation term which is minus EER cosine theta and psi 100 r. Now, you have to be careful in writing this integration, or rather the dr. In 1D we can simply write as dx, but this problem has spherical symmetry. So, you have to write a dv, so it has to be integrated over all volume, and that tells us that if you write a dv, then a dv is written as r squared dr sine theta d theta and d phi. Okay. And this r goes from 0 to infinity. Okay. It goes all the way from 0 to infinity, theta goes from 0 to pi, and phi goes from 0 to 2 pi. Okay. So, there without really doing everything, because there is an R integral psi 1 0 0 does not depend upon theta or phi. The phi integral is trivial here because there is no phi term there. So, we can take this 2 pi out, and so the only you have to look at before you do the R integral. Let us look at the theta integral, and the theta integral is cos theta d theta, and you have a sin theta because there is a sin theta here. So, sin theta cos theta sin theta d theta, and this is from 0 to pi. Now, you see that what you can do is that either you show that this is equal to 0, or you can write the sin theta d theta as a d of cos theta, and then this limit goes from -1 to +1, and you can still show that it is equal to 0. So, we have a cos theta d of cos theta, and then this integral really goes from -1 to +1, it is again equal to 0. So, that gives us a lesson that the first order energy correction to the ground state of hydrogen atom is 0 due to a weak electric field. Okay. So, it says first order Stark effect on the ground state vanishes. This is an important result, and you may be asked a question, say a multiple choice question, that what is the value in this, and just keep this result in mind, and the result comes because of this theta integral. All the other integrals are non-zero. Okay. So, there is no shift in energy because of this electric field to the ground state. So, to see what really exists, so we have two options. We can look at the second order correction to energy in the ground state, which is going to be a more difficult problem. I will not do that problem, but I will simply state the result. But a more doable problem, and which is more relatable to what we have just discussed about the degenerate perturbation theory, is the first order Stark effect on the first excited state. All right. So, now this is important because the first excited state, which is n equal to 2, is really fourfold degenerate, because it is n square fold degenerate. So, we have a real degenerate problem, degenerate perturbation theory problem, and that will tell us that whether we will have a shift in energy, or we do not have a shift in energy, whether there is a complete removal of degeneracy, or there is just a partial removal of degeneracy. Okay. So, there are 4 states, and what are those 4 states? Because if n is equal to 2, L can take values 0 and 1, and ML can correspondingly take values which are if L is 0, ML is 0, if L is 1, ML is 1 or 0 or -1. So, we have how many states that we have now? So, we have 2, n equal to 2, L equal to 0, ML equal to 0. This is called as a psi 200 state in our notation that we use, psi NLM, and if n equal to 2, then L equal to 1. So, we have L equal to 1, we have ML which can be equal to 1, and let us call that as psi 211. We will use them in some order while doing the calculation, and then we have 2 and then 1 and 0. So, this we call psi 210, and then again we have the other one as 2, 1 and minus 1, and we call it a psi 2, 1 minus 1 r. And this fellow is called as the S state. S corresponds to this notation when L is equal to 0, this angular momentum, this quantum number is equal to 0, the azimuthal quantum number, and these are called as the P states. Okay. And P states are 3 of them, and each one of them have an energy which is equal to E2, which is equal to minus 3.4 electron volt, which comes from nothing but 13.6 divided by 4. Okay. So, that is the each one of them are having this energy. Okay. So, we will call this as so now let me change this order a little in order to have a consistency with the notation that I am using. So, let us call a U1 R to be equal to psi 200, that is the notation that we have used earlier, this U1, U2 etc. And explicitly writing what these are, this you can look at any book and get these explicit forms. We have shown them by plots and sometimes have even written them down, but there is no need to remember them, because if there is a accepting maybe the ground state you should remember, which is what we have just shown here, which is this 1 by root over pi a0 cube exponential minus r by a0. The others will most likely will be supplied. So, this 2 r by a0 exponential r by 2 a0 and so on, and u2 r, this is equal to psi. Now, this I do not use the this ordering that we have done. So, we write it 2 1 0. So, this is equal to 1 by 4 root over 2 pi r over a naught cosine theta exponential r over 2 a naught. You see, the L equal to 0 does not have any theta or phi dependence, whereas if L is not equal to 0, then it has a theta dependence. In addition, if M is not equal to 0, it also has a phi dependence. U3 R, this is equal to psi 2 1 1, and this is equal to 1 by 8 root pi 1 over a0 whole to the power 3 by 2 sine theta e to the power I phi e to the power minus r by 2 a0. And finally, we have the u4, which is the last one, which is 2 1 minus 1 r, and so there is a 1 by 8 root pi which is 1 over a0 3 by 2 sine theta, and now we have an exponential minus I phi, and that is why they are bunched together. It is r over 2 a0. All right. So, these are the 4 eigenstates, and then the solution is clear because we have laid down the basis for this problem, and you have to calculate how many of these matrix elements really. There are 4 into 4, 16 matrix elements, which are all these H prime ij's, and before you actually go ahead and calculate all of them, you would be able to appreciate that some of them simply goes to 0 without doing a calculation, and we will see that. So, the first order energy correction is obtained as from this equation, which is Hij prime minus En1. And of course, we should write because Hij prime is okay, it is not that required, but you can just say that determinant of this is equal to 0. Okay. So, I just put this identity matrix because it is there everywhere along the diagonal part. So, just to make sure that that information is carried. So, this is the you have to do it for the 4-fold degenerate problem, and exactly what has been shown. So, you have to solve a 4 by 4 determinant, putting that equal to 0, but you may be lucky enough not to have a 4 by 4 problem to be solved in its entirety. What could happen is that some of the elements would be 0 in such a fashion that you have a block of 2 by 2. If that happens, then of course, that is the best thing that you are looking for. So, if you look for this H11 prime, that is the matrix elements of the perturbation term between these U1 terms. Now, you see that U1 term does not have any theta. So, the only theta will come from the sine theta d theta from 0 to pi, which is equal to 0. Okay, so, H11 prime will be 0 because you have cosine theta d of cosine theta, which is minus 1 to plus 1, which is the same as sine theta d theta, from 0 to pi, this is equal to 0 and so on. So, only theta integral gives 0. So, what about H22 prime? That is the one that you have. Now, you see H22 prime will have a cosine theta there, and this I have written it in the sense that so there is a sine theta cos theta. So, there is a kind of sine theta coming from this integral, and then there is a cos theta which I forgot to write. So, this is there, and H22 prime will have a minus 1 to plus 1 and a cos cube of theta d of cos theta. So, just take cos theta as some x variable. So, it is x cube dx from minus 1 to plus 1, that will again be 0, and similarly the H33 prime, again because of all these the theta integral. I am not saying they are equal, but they both are 0. That is what I am trying to show. So, if the equality sign bothers you, then you can say both. So, we can write it separately. So, this is equal to 0 to pi, again a sine square theta, a cos theta, that is d theta, that is equal to 0, and similarly H44 prime is equal to 0 as well, okay, for the same reason. So, all the diagonal terms are 0. So, you are maybe lucky, but not so much, because you want the off diagonal terms to vanish, because in order for this size of the 4 by 4 matrix to come down, and you are probably lucky there as well, because if you see you have H13 prime, which means nothing but U1 H prime U3, and which means nothing but U1 star H prime, which is nothing but my this E cosine theta U3, and then you have a r squared dr sine theta d theta and d phi. And this is again it is equal to 0, because now because of the phi integral. So, the phi integral makes it 0, because 3 has a phi which is d phi e to the power I phi, and from 0 to 2 pi, because of this phase phi being 2 pi symmetric, which means that exponential phi equal to 0 and phi equal to 2 pi, they are same. So, this is equal to 0, and that is the same reason that your H14 prime equal to 0 as well, because of this reason that 0 to 2 pi d phi e to the power minus I phi, that is also equal to 0. You can show similarly that there are other terms which are so H24 prime, H42 prime equal to H34 prime, all of these equal to 0, and for this particular case, and you are only left with H12 prime and H21 prime are only non-zero. Okay. If that is the case, we have to calculate H12 prime and H21 prime. Now, you see that in this equation, that we have, that entirely the lower block is 0, and all the these one on the right, this block, let me show it by a laser pointer. So, this block is 0, this block is 0, all these diagonal terms are 0, leaving you with only E1 here and E1 here. The only non-zero terms, diagonal terms are 0 here as well. The only non-zero terms that exist are H12 prime and H21 prime, and that is what we are trying to calculate now. Okay. So, H12 prime is equal to E divided by 32 pi epsilon 0. So, we are taking the overlap of this perturbation term between U1 and U2. So, 32 pi, and then you have a 0 to infinity 2 minus r by a 0 and r by a 0, and then you have a r cube exponential minus r over a 0, and then you have a minus 1 to 1 cosine square. Now, the cosine does not let you go to 0 because of this even power of cosine theta and d of cosine theta. So, we write down this theta integral usually because there is a sine theta cos theta, we write it in terms of cos square theta d of cos theta and so on, and then d phi is simply from 0 to pi. Okay. So, this is the r integral, theta integral and phi integral that you see there. From the theta integral, it is easy to see that you get a factor of 2 by 3, and a little bit of simplification can be done. So, E epsilon by 16 and it becomes 2 by 3, and the phi integral will give you a 2 pi. So, you have a 2 pi there. So, 2 pi cancels with this pi here and makes it a 16 in the denominator, and now we have these 1 over a naught, and you have a 0 to infinity r to the power 4 e to the power minus r by a naught dr, and a minus 1 by a 0 square and 0 to infinity, and you have a r to the power 5 e to the power minus r by a 0 dr and so on. So, this integral has to be solved, and what can be done is that you can use gamma function form. So, gamma of n, this is equal to 0 to infinity, this is called as a gamma function integral r to the power n minus 1 e to the power minus r dr, this is equal to gamma n, and gamma function has some property. So, one can actually do this simplification. Now, this equation or rather this integral is given to you. So, you can write it down in terms of these. So, H12 prime becomes minus 3 E a 0, and when you calculate the H21 prime, it of course gives you the same result because it is simply the perturbation term does not alter the ket or the wave function that is coming on its right. So, this will be same, and let us call this as alpha. I mean, basically just not to carry around this factor every time. Now, what happens is that if you look at this lower block, this block does not yield anything. That is, it gives you the eigenvalues of this is equal to 0, and this becomes just an upper block on the left and a lower block on the right, and the lower block on the right gives you two corrections to be equal to 0, which means that we have E231 is equal to E241 is equal to 0, which means that there is a partial removal of degeneracy. That means this fourfold degenerate, two of them continues to be degenerate even in the presence of this perturbation term, and the other two gets they sort of degeneracy is removed, and what you have is that pictorially we have a 4-fold degenerate. So, this 4 lines that you see merging together, that tells you that the unperturbed this thing. So, it continues to be a 2-fold degenerate, and this 2, okay, and this shift is calculated using so one of them will like shift upward and the other will shift downward and so on. So, this n equal to 2 and these are proportional to this alpha. Okay. So, we can actually because of this simple a feature that the 4 by 4 matrix splits into 2 by 2 block matrices, one can calculate the eigenfunctions corresponding to that, and you use this alpha and write this as A11 minus alpha A21 minus alpha A. So, this is equal to 0 and A11 plus alpha A21 is equal to 0. So, that tells you that A11 is equal to A21. So, the bottommost level you see here, that corresponds to so, this one that you see here corresponds to this psi 1 or rather psi 210. This is equal to A11 U1 plus A21 U2. This is equal to A11 U1 plus U2. That is the this is the bottommost level, that is the let us call this as 2, 3, 1 and 4. Okay. So, as if all these 4 were there, but do not confuse this with U1 and U2, like they are not U1, U2, U3, U4, but the fourth one, that is a bottommost one, is a combination of U1 and U2 in this particular fashion. And so, it is easy to normalize it, because there are 2 functions and this has to be normalized. So, your psi 210, this is equal to 1 by root 2 U1 plus U2, that is the lowest one. And for the topmost level, we have the other 2 equations corresponding to these the changes in the energy, and this is alpha A12 minus alpha A22, this is equal to 0, and minus alpha A12 minus alpha A22, this is equal to 0 as well. So, we have then this has A12 equal to minus A22 minus A22. So, the bottom the topmost level, this is the topmost level, this is equal to psi 220, this is equal to 1 by root 2 U1 minus U2. Okay. So, there is a partial removal of degeneracy. Two levels continue to be degenerate and so on. And so, let me write down the summary of these results that you have seen here, and the summary says that for the purely S wave state, Stark effect is 0, which means that there is no change in energy. So, Stark effect gives 0. Okay. So, for n equal to 2, so this is for n equal to 1. So, for n equal to 2, which are combinations of S and P, this Stark effect gives partial removal of degeneracy. So, it is important to understand that this degeneracy is only removed when S is coupled to P. So, let me show this. So, S is this U1 state, right, and all these are P states. So, P corresponds to this U2, U3 and U4. So, the matrix elements of H prime between this and between this and between this, they are all 0. So, all these are 0 and the only one that is non-zero is this one. So, that tells you that when the ML value or M value rather, the magnetic quantum number changes by 1, then the Stark effect actually gives a removal of degeneracy. And this can be easily understood if you really think that the H prime term, which is proportional to the cosine theta. Now, the cosine theta according to the theory of angular momentum, it looks like Z. So, that tells you that so Lz is like minus IH cross del phi, that is the form. So, H prime is like Z. So, H prime and Lz, they commute, and that means the Ui and H prime Lz that also becomes equal to 0 between two states, right. So, let us say Ui is like Y LML, LM sorry, not ML, I mean sometimes because of these the other quantum number that is J corresponding to the total angular momentum. So, we use a MJ, but that is not a case here. And then this is say the other one is like the Y L prime M prime. Okay. So, these thing will become equal to is M prime minus M and then Ui H prime Uj. Okay. Now, this is equal to 0 for M when M is not equal to M prime, but this is 0, okay, but M not equal to M prime, that is one of them. So, it is not 0 because of that, but it is 0 because of this, and in the other case this is equal to 0 when M equal to M prime, and that is why all these are 0 excepting the one. See, 3 and 4 is 0 because M is equal to M prime, we do not have to have the other, the matrix element to be equal to 0, but not true for M equal to 0. So, that is the one that gives you contribution between U1 and U2, which corresponds to psi 200 and this corresponds to psi 210, and that is where you have a non-zero contribution coming from. Okay. Now, I will skip, as I said, this the second order Stark effect in the ground state because it is mathematically complicated, but I will just simply state the final result, and the final result tells you that so what about second order Stark effect in ground state. And the answer is that En2, that is the second order correction in energy to the ground state, is actually a minus, can be written as minus alpha induced, this is called as the induced electric dipole moment, and is proportional to the as expected, proportional to the square of the electric field. Of course, if electric field is weak, the second order should be even smaller, and this alpha end is equal to the induced dipole moment and this is has a value which is 9 over 2 A0 cube, where A0 is the Bohr radius. Okay. So, though atomic hydrogen do not have a permanent dipole moment, the induced dipole moment of course exists in presence of a Prof, an electric field. Okay. And as I said that I do not give a derivation of this, but it's not undoable. It's a long derivation, but it's good enough for you that if you remember, that is En2, that's the second order on the ground state. This is nothing but minus 9 over 4 A0 cube E square. So, there is a change in the eigen value or rather the energy eigenvalue because of this energy correction, and it will shift from its position minus 13.6. So, and in the ground state it will be En equal to En0 minus, so this En0 is minus 13.6 electron volt and plus a 9 over 4 A0 cube E square. Okay. So, it will shift up by this amount, and because of this induced dipole moment. Okay. So, we have talked about degenerate perturbation theory and have talked about how the Stark effect can be analyzed, and that the first order Stark effect on ground state equal to 0, and that happens because your the orbital S orbital is spherically symmetric. So, the electric field which tries to create a dipole moment on a spherically symmetric orbital, it does not have any effect. And we saw it for the first order Stark effect in the first excited state. There we have seen that it is only when S couples to P, S state couples to the P state, then you have a change in correction, or so there is a partial removal of degeneracy. Two of the levels continue to have the same energy, and the other two shift symmetrically up or down compared to the minus 3.4 electron volt. And there is also a second order Stark effect, finite second order Stark effect on the ground state of the hydrogen atoms. So, we will stop here and continue with more applications of perturbation theory in the coming class. Thank you.